Stereoscopy is a technique for creating or enhancing the illusion of depth in an image by means of stereopsis for binocular vision. The word stereoscopy derives from Greek sigma tau epsilon rho epsilon omicron sigma, meaning firm, solid, and sigma kappa omicron pi epsilon omega, meaning to look to see. Any stereoscopic image is called a stereogram. Originally, stereogram referred to a pair of stereo images which could be viewed using a stereoscope. Most stereoscopic methods present two offset images separately to the left and right eye of the viewer. These two-dimensional eye images are then combined in the brain to give the perception of 3D depth. This technique is distinguished from 3D displays that display an image in 3 full dimensions, allowing the observer to increase information about the 3-dimensional objects being displayed by head and eye movements. Background. Stereoscopy creates the illusion of 3-dimensional depth from given 2-dimensional images. Human vision, including the perception of depth, is a complex process, which only begins with the acquisition of visual information taken in through the eyes. Much processing ensues within the brain, as it strives to make sense of the raw information. One of the functions that occur within the brain as it interprets what the eyes see is assessing the relative distances of objects from the viewer, and the depth dimension of those objects. The cues that the brain uses to gauge relative distances and depth in a perceived scene include stereopsis, accommodation of the eye, overlapping of one object by another, subtended visual angle of an object of known size, linear perspective, vertical position, hazer contrast, saturation, and color. Greater distance generally being associated with greater haze, desaturation, and a shift toward blue. Change in size of textured pattern detail. Stereoscopy is the production of the illusion of depth in a photograph, movie, or other two-dimensional image by the presentation of a slightly different image to each one, which adds the first of these cues. The two images are then combined in the brain to give the perception of depth. Because all points in the image produced by stereoscopy focus at the same plane regardless of their depth in the original scene, the second cue, focus, is not duplicated and therefore the illusion of depth is incomplete. There are also mainly two effects of stereoscopy that are unnatural for human vision: the mismatch between convergence and accommodation, caused by the difference between an object's perceived position in front of or behind the display screen and the real origin of the light, and possible crosstalk between the eyes, caused by imperfect image separation in some methods of stereoscopy. Although the term 3D is ubiquitously used, the presentation of dual 2D images is distinctly different from displaying an image in 3 full dimensions. The most notable difference is that, in the case of 3D displays, the observer's head and eye movement do not change the information received about the 3-dimensional objects being viewed. Holographic displays and volumetric display do not have this limitation. Just as it is not possible to recreate a full 3-dimensional sound field with just 2 stereophonic speakers, it is an overstatement to call dual 2D images 3D. The accurate term, stereoscopic, is more cumbersome than the common misnomer 3D, which has been entrenched by many decades of unquestioned misuse. Although most stereoscopic displays do not qualify as real 3D display, all real 3D displays are also stereoscopic displays because they meet the lower criteria also. Most 3D displays use this stereoscopic method to convey images. It was first invented by Sir Charles Wheatstone in 1838, and improved by Sir David Brewster, who made the first portable 3D viewing device. Wheatstone originally used his stereoscope with drawings because photography was not yet available, yet his original paper seems to foresee the development of a realistic imaging method. For the purposes of illustration I have employed only outline figures. Had either shading or coloring been introduced, it might be supposed that the effect was wholly or in part due to these circumstances, whereas by leaving them out of consideration no room is left to doubt that the entire effect of relief is owing to the simultaneous perception of the two monocular projections, one on each retina. But if it be required to obtain the most faithful resemblances of real objects, shadowing and coloring may properly be employed to heighten the effects. Careful attention would enable an artist to draw and paint the two-component pictures, so as to present to the mind of the observer, in the resultant perception, perfect identity with the object represented. Flowers, crystals, busts, vases, instruments of various kinds, and C might thus be represented so as not to be distinguished by sight from the real objects themselves. Stereoscopy is used in photogrammetry and also for entertainment through the production of stereograms. Stereoscopy is useful in viewing images rendered from large multi-dimensional data sets such as are produced by experimental data. An early patent for 3D imaging in cinema and television was granted to physicist Theodore V. Ionescu in 1936. Modern industrial three-dimensional photography may use 3D scanners to detect and record three-dimensional information. The three-dimensional depth information can be reconstructed from two images using a computer by corresponding the pixels in the left and right images. Solving the correspondence problem in the field of computer vision aims to create meaningful depth information from two images. Visual requirements. Anatomically, there are three levels of binocular vision required to view stereo images: simultaneous perception, fusion, stereopsis. These functions develop in early childhood. Some people who have strabismus disrupt the development of stereopsis. However, orthopedic treatment can be used to improve binocular vision. A person's stereo acuity determines the minimum image disparity they can perceive as depth. It is believed that approximately 12% of people are unable to properly see 3D images due to a variety of medical conditions. According to another experiment, up to 30% of people have very weak stereoscopic vision, preventing them from depth perception based on stereo disparity. This nullifies or greatly decreases immersion effects of stereo to them. Side by side. Traditional stereoscopic photography consists of creating a 3D illusion starting from a pair of 2D images, a stereogram. The easiest way to enhance depth perception in the brain is to provide the eyes of the viewer with two different images, representing two perspectives of the same object, with a minor deviation equal or nearly equal to the perspectives that both eyes naturally receive in binocular vision. To avoid eye strain and distortion, each of the two 2D images should be presented to the viewer so that any object at infinite distance is perceived by the eye as being straight ahead, the viewer's eyes being neither crossed nor diverging. When the picture contains no object at infinite distance, such as a horizon or a cloud, the pictures should be spaced correspondingly closer together. The principal advantages of side-by-side viewers is the lack of diminution of brightness, allowing the presentation of images at very high resolution and in full spectrum color, simplicity in creation, and little or no additional image processing is required. Under some circumstances, such as when a pair of images are presented for free viewing, no device or additional optical equipment is needed. The principal disadvantage of side-by-side viewers is that large image displays are not practical and resolution is limited by the lesser of the display medium a human eye. This is because as the dimensions of an image are increased, either the viewing apparatus or viewer themselves must move proportionately further away away from it in order to view it comfortably. Moving closer to an image in order to see more detail would only be possible with viewing equipment that adjusted to the difference. Free viewing is viewing a side-by-side image pair without using a viewing device. Two methods are available to free view. The parallel viewing method uses an image pair with the left eye image on the left and the right eye image on the right. The fused three-dimensional image appears larger and more distant than the two actual images, making it possible to convincingly simulate a life-size scene. The viewer attempts to look through the images with the eyes substantially parallel, as if looking at the actual scene. This can be difficult with normal vision because eye focus and binocular convergence are habitually coordinated. One approach to decoupling the two functions is to view the image pair extremely close up with completely relaxed eyes, making no attempt to focus clearly but simply achieving comfortable stereoscopic fusion of the two blurry images by the look-through approach, and only then exerting the effort to focus them more clearly, increasing the viewing distance as necessary. Regardless of the approach used to the image medium, for comfortable viewing and stereoscopic accuracy, the size and spacing of the images should be such that the corresponding points of very distant objects in the scene are separated by the same distance as the viewer's eyes, but not more. The average interocular distance is about 63 mm. Viewing much more widely separated images is possible, but because the eyes never diverge in normal use, it usually requires some previous training and tends to cause eye strain. The cross-eyed viewing method swaps the left and right eye images so that they will be correctly seen cross-eyed, the left eye viewing the image on the right and vice versa. The fused three-dimensional image appears to be smaller and closer than the actual images, so that large objects and scenes appear miniaturized. This method is usually easier for free viewing novices. As an aid to fusion, a fingertip can be placed just below the division between the two images, then slowly brought straight toward the viewer's eyes, keeping the eyes directed at the fingertip at a certain distance. A fused three-dimensional eye image should seem to be hovering just above the finger. Alternatively, a piece of paper with a small opening cut into it can be used in a similar manner. When correctly positioned between the image pair and the viewer's eyes, it will seem to frame a small three-dimensional image. Prismatic, self-masking glasses are now being used by some cross-eyed view advocates. These reduce the degree of convergence required and allow large images to be displayed. However, any viewing aid that uses prisms, mirrors or lenses to assist fusion of focus is simply a type of stereoscope, excluded by the customary definition of free viewing. Stereoscopically fusing two separate images without the aid of mirrors or prisms while simultaneously keeping them in sharp focus without the aid of suitable viewing lenses inevitably requires an unnatural combination of divergence and accommodation. Simple free viewing therefore cannot accurately reproduce the physiological depth cues of the real-world viewing experience. Different individuals may experience differing degrees of ease and comfort in achieving fusion and good focus, as well as differing tendencies to eye fatigue or strain. Autostereogram. An autostereogram is a single-image stereogram, designed to create the visual illusion of a three-dimensional scene within the human brain from an external two-dimensional image. In order to perceive 3D shapes in these autostereograms, one must overcome the normally automatic coordination between focusing and divergence. Stereoscope and stereographic cards. The stereoscope is essentially an instrument in which two photographs of the same object, taken from slightly different angles, are simultaneously presented, one to each eye. A simple stereoscope is limited in the size of the image that may be used. A more complex stereoscope uses a pair of horizontal periscope-like devices, allowing the use of larger images that can present more detailed information in a wider field of view. Transparency viewers. Some stereoscopes are designed for viewing transparent photographs on filmy glass. Known as transparencies are diapositives and commonly called slides. Some of the earliest stereoscope views, issued in the 1850s, were on glass. In the early 20th century, 45 by 107 mm and 6 by 13 cm glass slides were common formats for amateur stereo photography, especially in Europe. In later years, several film-based formats were in use. The best-known formats for commercially issued stereo views on film are TruView, introduced in 1931, and ViewMaster, introduced in 1939 and still in production. For amateur stereo slides, the stereo realist format, introduced in 1947, is by far the most common. Head-mounted displays. The user typically wears a helmet, glasses with two small LCD or OLED displays with magnifying lenses, one for each eye. The technology can be used to show stereo films, images or games, but it can also be used to create a virtual display. Head-mounted displays may also be coupled with head-tracking devices, allowing the user to look around the virtual world by moving the head, eliminating the need for a separate controller. Performing this update quickly enough to avoid inducing nausea in the user requires a great amount of computer image processing. If 6-axis position sensing is used, the wearer may move about within the limitations of the equipment used. Owing to rapid advancements in computer graphics and the continuing miniaturization of video and other equipment, these devices are beginning to become available at more reasonable cost. Head-mounted or wearable glasses may be used to view a see-through image imposed upon the real-world view, creating what is called augmented reality. This is done by reflecting the video images through partially reflective mirrors. The real-world view is seen through the mirror's reflective surface. Experimental systems have been used for gaming, where virtual opponents may peek from real windows as a player moves about. This type of system is expected to have wide application in the maintenance of complex systems, as it can give a technician what is effectively X-ray vision, by combining computer graphics rendering of hidden elements with the technician's natural vision. Additionally, technical data and schematic diagrams may be delivered to this same equipment, eliminating the need to obtain and carry bulky paper documents. Augmented stereoscopic vision is also expected to have applications in surgery, as it allows the combination of radiographic data with the surgeon's vision. Virtual retinal displays. A virtual retinal display, also known as a retinal scan display, a retinal projector, not to be confused with a retina display, is a display technology that draws a raster image directly onto the retina of the eye. The user sees what appears to be a conventional display floating in space in front of them. For true stereoscopy, each eye must be provided with its own discrete display. To produce a virtual display that occupies a usefully large visual angle but does not involve the use of relatively large lenses or mirrors, the light source must be very close to the eye. A contact lens incorporating one or more semiconductor light sources is the form most commonly proposed. As of 2013, the inclusion of suitable light beams cutting means in a contact lens is still very problematic, as is the alternative of embedding a reasonably transparent array of hundreds of thousands of accurately aligned sources of collimated light. 3D viewers. There are two categories of 3D viewer technology: active and passive. Active viewers have electronics which interact with the display. Passive viewers filter constant streams of binocular input to the appropriate eye. Active shutter systems. A shutter system works by openly presenting the image intended for the left eye while blocking the right eye's view, then presenting the right eye image while blocking the left eye, and repeating this so rapidly that the interruptions do not interfere with the perceived fusion of the two images into a single 3D image. It generally uses liquid crystal shutter glasses. Each eye's glass contains a liquid crystal layer which has the property of becoming dark when voltage is applied, being otherwise transparent. The glasses are controlled by a timing signal that allows the glasses to alternately darken over one eye and then the other, in synchronization with the refresh rate of the screen. The main drawback of active shutters is that most 3D videos and movies were shot with simultaneous left and right views, so that it introduces a time parallax for anything side-moving. For instance, someone walking at 3.4 miles per hour will be seen 20% too close or 25% too remote in the most current case of a 2 by 60 Hz projection. Passive polarization systems to present stereoscopic pictures. Two images are projected superimposed onto the same screen through polarizing filters are presented on a display with polarized filters. For projection, a silver screen is used so that polarization is preserved. On most passive displays, every other row of pixels are polarized for one or the other. This method is also known as being interlaced. The viewer wears low-cost eyeglasses which also contain a pair of opposite polarizing filters. As each filter only passes light which is similarly polarized and blocks the opposite polarized light, each eye only sees one of the images, and the effect is achieved. Interference filter systems. This technique uses specific wavelengths of red, green, and blue for the right eye, and different wavelengths of red, green, and blue for the left eye. Eyeglasses which filter out the very specific wavelengths allow the wearer to see a full-color 3D image. It is also known as spectral comb filtering, a wavelength multiplex visualization, a superanaglyph. Dolby 3D uses this principle. The Omega 3D, Panavision 3D system has also used an improved version of this technology. In June 2012, the Omega 3D, Panavision 3D system was discontinued by DPVO Theatrical, who marketed it on behalf of Panavision, citing challenging global economic and 3D market conditions. Although DPVO dissolved its business operations, Omega Optical continues promoting and selling 3D systems to non-theatrical markets. Omega Optical's 3D system contains projection filters and 3D glasses. In addition to the passive stereoscopic 3D system, Omega Optical has produced enhanced anaglyph 3D glasses. The Omega's red, cyan anaglyph glasses use complex metal oxide thin film coatings and high-quality annealed glass optics. Color anaglyph systems. Anaglyph 3D is the name given to the stereoscopic 3D effect achieved by means of encoding each eye's image using filters of different colors, typically red and cyan. Red-cyan filters can be used because our vision processing systems use red and cyan comparisons, as well as blue and yellow, to determine the color and contours of objects. Anaglyph 3D images contain two differently filtered colored images, one for each eye. When viewed through the color-coded anaglyph glasses, each of the two images reaches one eye, revealing an integrated stereoscopic image. The visual cortex of the brain fuses this into perception of a three-dimensional scene composition. Chroma depth system. The chroma depth procedure of American paper optics is based on the fact that with a prism, colors are separated by varying degrees. The Chroma depth eyeglasses contain special view foils, which consist of microscopically small prisms. This causes the image to be translated a certain amount that depends on its color. If one uses a prism foil now with one eye but not on the other eye, then the two seen pictures, depending upon color, are more or less widely separated. The brain produces the spatial impression from this difference. The advantage of this technology consists above all of the fact that one can regard chroma depth pictures also without eyeglasses problem-free. However, the colors are only limitedly selectable, since they contain the depth information of the picture. If one changes the color of an object, then its observed distance will also be changed. Wulfric Method. The Wulfric effect is based on the phenomenon of the human eye processing images more slowly when there is less light, as when looking through a dark lens. Because the Wulfric effect depends on motion in a particular direction to instigate the illusion of depth, it is not useful as a general stereoscopic technique. For example, it cannot be used to show a stationary object apparently extending into or out of the screen. Similarly, objects moving vertically will not be seen as moving in depth. Incidental movement of objects will create spurious artifacts, and these incidental effects will be seen as artificial depth not related to actual depth in the scene. Over/under format. Stereoscopic viewing is achieved by placing an image pair one above one another. Special viewers are made for over/under format that tilt the right eyesight slightly up and the left eyesight slightly down. The most common one with mirrors is the ViewMagic. Another with prismatic glasses is the KMQ viewer. A recent usage of this technique is the OpenKMQ project.